Hi, my name is Imran Yusuf, and I am joined by my colleagues Pankaj and Sashi from Cadence. Cadence and ARM have a long and rich history of collaboration, and in our presentation today, we're pleased to discuss enabling shift left for SBSA tests using bare metal adaptation on emulation. The agenda for our discussion, I will start it off and discuss ARM SystemReady program and our SBSA Pre-Silicon collaboration with Cadence. And then I'll hand it over to my colleagues from Cadence. We'll be talking about compliance, pre-silicon bring-up flow, and talk about the Cadence solution, and share with you a very cool demo. And then we'll end it with a call to action. We at ARM are excited to launch our SystemReady program at the DevSummit. SystemReady is a foundational program that's built upon standards, architecture standards, that has a vision so that software can just work on ARM-based devices. The underpinning of this program are hardware and firmware specifications that allow common OSs to just boot on ARM devices. The value that this brings to our ecosystem is that it provides interoperability and portability. It increases the time to market for our ecosystem, and it's also a TAM expansion opportunity as they can enter different markets, as you can see, from server, cloud, data centers, all the way to the infrastructure edge and IoT. An integral part of our collaboration with SystemReady is around pre-silicon compliance with Cadence. ARM is pleased to offer pre-silicon BSA compliance certification for designs passing compliance in pre-silicon. A lot is at stake here. The majority of the silicon today is non-compliant, and each ARM device, while unique, while it's unique, it has inherent advantages. Today, we have no pre-silicon compliance validation process that ensures operating systems will just work prior to tape out. This is where the collaboration with Cadence brings tremendous benefits for our ecosystem. It reduces the developer's risk by catching BSA compliance bugs before tape out. It ensures by running bare metal that operating systems off the shelf can boot and function without any custom patches. And this minimizes potential design respins in the future. It also makes the product more robust and attractive, and the addressable market consequently also expands by being able to have multiple OSs and the workloads that run on these OSs work seamlessly. As I mentioned, the underpinning and then the key pillars of this of our program are the hardware specification and the firmware specification. The base system architecture specification documents a minimal set of CPU and system architecture requirements for an OS to boot and run. Similarly, we have firmware requirements that need to be met in order for the operating systems to just boot without any modifications or kernel updates. We also have market-specific hardware supplements such as the SBSA, which is our server-based system architecture that comprehends an increasing set of hardware features that are attributed to the progression of the CPU and the architecture. We'll be launching this program that includes four bands. Today, we already have the server-ready band that was launched 2 years ago, and included in our system-ready bands are the Linux boot, the ES, which is the embedded server boot, and the IR, which is the IoT boot. The value that customers derive from these different bands is that they can certify their devices depending on the market requirements of their product. For example, the SR band covers most of the data center use cases. The embedded server covers the infrastructure edge, and the IR band covers most of the IoT use cases. We're pleased to include the pre-silicon certification as part of SystemReady. The value that our partners can derive from this is to be able to certify their SoCs prior to tape out. And this creates benefits, as I mentioned before, around time to market advantages, being able to catch errors and bugs prior to tape out, minimize design spins. And we believe that this is going to provide a tremendous advantage for our partners in terms of being able to get to market faster and expanding their markets. I'm now going to hand off to my colleague Pankaj to talk more about the Cadence solution.
Thanks, Imran. I am Pankaj, Solutions Group Director at Cadence, and I'm going to give you a brief overview of what the Cadence Pre-Silicon solution is. Currently, it's targeted for server-based system architecture compliance, and it's expected to expand into the overall system-ready space. The first part that we are focused on is to enable server-ready with the server-based system architecture compliance. So typically, what customers have been doing is the certification is mostly done post-silicon. So as you would see in this time bar chart, the certification typically is done by customers running the certification tests that ARM provides post-silicon. I mean, there are tests that you can also run once you have Linux brought up on your SoC, but that happens pretty late in the cycle. Either after tape out or very close to tape out. So if you find issues or hardware issues that you really need to fix, it becomes too late. So what Cadence brings an offering here is to enable the checking of the system architecture rules for server much earlier in the cycle, wherein as your SoC RTL starts to become ready, and you have this working on a hardware emulator like Cadence Palladium, you essentially can run the ARM compliance tests that are all available from ARM using a bare metal software and the unique solution that Cadence brings with a controllable PCIe endpoint, because there are a lot of rules that are getting added around PCIe, which add a lot of complexity and are very hard to verify on top of Linux, or almost impossible to do post-silicon. So basically what we have done in collaboration with ARM is build the solution which allows you to do pre-silicon compliance much earlier in your cycle, so that if you are compliant, you go through the pre-silicon certification process with ARM, share the logs, and basically can feel confident that once your SoC goes out into silicon, when you bring up the OSs, you wouldn't really need to add costly patches and add delays. Okay. All right. So let me take you through an example of how we really enable pre-silicon compliance using the Cadence solution. So what you see here is a very representative server SoC, a very simplified block diagram with a system interconnect, a DDR controller, CPU, interrupt controller, system MMU, PCIe, root board or root complex, depending on what your device has. It could be one or multiple. What we do as part of the Cadence solution is we offer the controllable endpoint, which is our PCIe accelerated VIP. And this stack that is here on the top, coming from SBSA Architecture Compliance Suite, and then these layers of abstraction essentially are coming from ARM. So all this blue boxes come from ARM. ARM does provide the UEFI and PAL implementation, which allows you to run these tests on top of Linux or UEFI. What we do as Cadence is we provide you a BM-PAL layer, which allows you to run on bare metal pre-silicon on an emulator. So we provide you the bare metal adaptation, we provide you the required drivers for it, and we provide a controllable endpoint which allows you to run all the architecture compliance suite, which essentially would be running on your embedded CPU and would be doing the things that are required to talk to the PCIe, either the root port or the endpoint. Okay, so if I go on to my next slide, let me go into a little bit more detail of how we do this. So basically, I just simplified the SoC block diagram. So we have this blue boxes which are available from ARM. So the tests and the rules for architecture compliance come from ARM. Cadence provides the bare metal adaptation, which has the necessary logic to run all the tests for the different peripherals, the processing elements, the interrupt controller, the SMMU related tests, and all the PCIe tests. So what will happen for a PCIe test is that we have this unique solution of allowing a PCIe test running on an embedded CPU to connect to the PCIe endpoint from the PCIe DUT. We also have the ability for the test to control the endpoint, which is our PCIe accelerated VIP. That's again available from Cadence. And with that, we are able to essentially control what the PCIe endpoint needs to do from the test that's running on the embedded CPU, and we have a unique mechanism to essentially enable that control of the test bench. And this control is very granular because we are able to do whatever we really want the endpoint to do, and that allows us to check for a lot of detailed and complex rules that are getting added as part of the pre-silicon compliance. And some of these aspects of controllability are not easily possible to do on top of Linux, and definitely not possible to do post-silicon. So if I talk about a few examples, so what's happening is as the SBSA rules are evolving, right now we are at ACS 2.4. There's 2.5 and 3.0 versions coming soon from ARM. There are a lot of checks related to enumeration, checks related to error handling, IO coherency, and that requires a lot of controllability of the endpoint, which is where it's not possible to do post-silicon. And that's where this solution becomes very unique, with the ability to enable validating these rules much earlier as part of your basic SoC verification on emulation. Okay, I'll not go into the details of these rules, but this is just some examples that are here, and the list is expanding. So just to briefly talk about where we are, so we do support ACS 2.4, which is available from ARM today. We are working with ARM to support 2.5. So this has rules from SBSA version 5.0 and 6.0 spec. With respect to the different components that are available in our customers' SoC, if they are using standard CPUs from ARM, the 8 or 8.2 cores, it should just work out of the box. I mean, there's no real porting required because we provide the required drivers to adapt the SBSA tests to run bare metal. And the same holds true for JIC, timer, other peripherals, watchdog, For PCIe, depending on the IP that you are using, if it's Cadence root port controller, things will work out of the box for you. But if you're using a third-party PCI IP, there will be certain PCIe functions like PCIe init, ability to enable memory read-write, config read-write is something that we will have APIs for, which we will have to implement in customers' IP bare metal environment. For the others, it should just work as long as customers are using the standard ARM architecture, like for interrupt controller. We have support for V3. We are working with ARM to extend this to V4 as well, for JIG, SMMU, and others. So I think we pretty much have the solution ready, which will enable customers to basically do this pre-silicon compliance out of the box. And with this, I'll hand over to my colleague Shashi to give you a quick demo of this running on a real server SoC on Palladium emulation.
Thanks, Imran and Pankaj. My name is Shashi. I work as Solutions Architect in Cadence. We have created a demo which demonstrates SBSA bare metal solution running in a pre-silicon environment on Palladium C1. So let's go and take a look at the demo. Hi, welcome to this demo of SBSA tests on bare metal. We have done two things here. We have compiled the design and loaded the design into Z1. The tests themselves takes around 30 to 40 minutes to run on Z1 for this design. So I have run the test for some time and paused the execution. So let's unpause the execution and let the test continue. So while the test continues to run, let's briefly look at the SBSA test suite and the models within the test suite, which have been adapted to enable SBSA tests to run in bare metal. Adaptation to run the tests on bare metal contains two parts. One is the software part and one is the test bench part. Let's first briefly go through the software adaptation for bare metal. As you can see on the screen, this is the listing of SBSA test suite. You can download the test suite from GitHub. For the sake of simplicity, we have kept the most relevant modules for this demo. The listing shows 4 main modules. The bare metal app. This is the entry point for the SBSA test, where the test related to each component being tested is called one after the other. The second important module is the test pool. This is where all the test logic implementation is present. The third module is the val layer, the validation abstraction layer. This sits between the test pool and the platform layer. So this is the core of the test framework. And the fourth module is the platform layer. This is where the test suite allows itself to be adapted to different platforms through relevant platform software. It comes by default with support to UEFI and Linux. And this is where we have extended the SBSA test suite to work in bare metal environment. Let's have a close look at the platform layer. So mainly it consists of PAL bare metal and bare metal software. So PAL bare metal consists of actual adaptation for different components tested by SBSA test suite. So let's list PAL bare metal. So in this listing, you see all the required test components modules for bare metal are implemented. So there is adaptation for each component tested by SBSA, like the processing elements, the PCIe, the I/O virtualization, etc. These modules connect through a well-defined APIs to the val layer. So the next important module here is the bare metal software. So it mainly consists of two directories or two modules, the first one being the driver module, the second one being the tools module. So driver modules contains all the bare metal driver implementation required by the respective SBSA components. So you can see from the listing that it has a driver for JIG, SMMU, SysTimer, etc. And the utils directory contains generic support functions which are used by one or more tests. So this is a very brief about the software adaptation. Now let's move to the test bench adaptation. So the test bench adaptation, test bench implementation contains the control logic which enables the SBSA tests to control or generate required traffic towards the system. This is done through a backdoor mailbox mechanism using perspec. Perspec mailbox plus the bare metal software adaptation together allows the SBSA test to control the traffic generation as required by the test. The test bench component implementation contains pre-written sequences which are executed to generate the required traffic towards the DUT system. So as you can see, this is the listing of the sequence modules or the test bench modules which have been implemented. They together represent, or they together give the full functionality to SBSA test suite to control the PCI AVIP endpoint to generate traffic towards the DUT. So this is a very brief about the adaptation we have done to enable SBSA tests to run on bare metal. So now let's go back to the tests and see the execution. So we've started some time before, it's executing. So as you can see, while it's executing, it's printing the status of the test executed. So you can see one of the tests has failed and many of them have passed. So this execution continues till all the tests are implemented. So we cannot see all the tests implemented here because with the interest of time, we cannot finish it within the time limit. But I do have run the entire test before this, and then I have generated the log which displays actually which tests have been run, what are the status of this. And as you can see while I'm scrolling, these are the different kinds of tests run. Like this is where the PE tests have started running, and then it continues to check all the required features which the SBSA tests defines. And then it makes sure it tries to run every test as defined. And then at the end, it gives you a result telling that these many tests were run and these many passed and these many failed. So in this case, 87 have passed and 4 tests have failed. And you can go back to the log and see which tests have failed. And I think the rest of the tests have been skipped because it's not supported on this particular design. So let's see if the tests are finished. So this will take a while. So I think we should pause the demo here. And thanks for listening. Thank you.
All right. So for our silicon partners with ARM extending the SystemReady and now extending it to Pre-Silicon, that's the first step to basically make sure that your SoC is compliant to the SystemReady architecture. And Cadence has a solution to enable this compliance pre-silicon, enable shift left for enabling early compliance for the SoCs that ARM customers and partners are building. So we are seeking some early access customers to work with on the solution that we have developed to enable early compliance for server-based system architecture. And if you are doing your SoCs and you're looking for making sure that you enable this early compliance and ensure that once you get your silicon out, it works out of the box, the operating systems work out of the box, we, along with ARM, have a solution that we can make that happen. So if you have more deeper questions, follow up, you can connect with my colleague Imran or myself. We have the email IDs here, and we would be glad to share more details with you and work with you to make sure that we enable you for the pre-silicon compliance and work with you early so that you can be confident once your silicon comes out, your operating systems will work out of the box on your silicon. So I think that's all we have on the presentation for today. Thank you.